think so.
Yeah, makes sense. I don't think I can go because I haven't go tournament.
It's a very good retirement town. Is it right? Durango.
Durango's a hippie town.
Oh my! So
Bayfield's a great place to retire, though.
Bayfield's good as well. Yeah.
What makes it a hippie town?
It has more dispensaries than churches.
Oh, that's awesome.
The average age of my neighborhood is about 75
That's
years
awesome.
old.
That's so funny. It's like how in Golden either you have three demographics, like high schoolers, college students, and then like 70-year-olds.
Yeah,
It's only one of those three.
High schoolers actually don't have parents either.
Yeah, they don't have parents, dude. I
Grown
swear.
in a tank.
Yeah, I also live like we both live like right across the street from the high school. Like it's weird like driving home and just seeing the children in front of the house.
There's a mob of
All right, let's get started.
every time.
One thing I missed last time. One really quick comment here. You press S, you turn on the flag, right? For lab 7. You press S, you turn on the flag. So when interrupts, it's going to pass that if statement. We'll get into all the other following states. So, however, there's one line of code in here showing that. Let me show the S part of it here. Right, so when you press S, it turns on the flag, and then it moves to the next state, the next line. So whenever it's true, it's gonna holding there, right? How do you get out from here?
Have the flag turned to false.
You have to turn over the flag, right? Turn the flag in where? In ISR. So I didn't cover that last time. So that's why some of the students are having issues because eventually it stuck as this while loop because it was not turned off. Where to turn it off? Just immediately after that if statement, checking, right? Whenever it checks if the flag's on, get into the if statement, turn it off. Make sense? So it's able to detect another flag on next time someone press S. All right. So turn it off, okay? Give a false to transmit IR state. I don't know where to draw it because there's no place, but you need to turn it off. Okay, keep that in mind. I'll give you guys several other options for the project because I was trying to be there yesterday for all the sections from like 8 a.m. Like I told you guys, I usually get up at 5, right? It's like from 5 a.m. to whatever, 6 or 7 p.m. This was a long day. Anyway, so I think I get a chance to talk with several students. Let me see if I can find that guy who talked about the thermostat. Are we here? We're not here. Okay, I'll just record it though. So there's one project you can work on because it's programming-wise, it's simple. So I'm going to require you to get the PCB out for sure. So one student asked if they can design a thermostat. It's a good project to think about. So when you are designing proposing your project, always consider that whenever someone interview you, how you would answer that question, right? So what kind of project you have worked on during undergraduate, and what kind of impact to the industry, right, of that project. Thermostat is great, right? If someone asks you what kind of project, you say, I designed a thermostat. Oh, sounds great. What kind of controller did you use? Right? How do you heat it up? How do you cool it down? So you have to answer all these kind of questions. Make sense? So if you want to design a thermostat, I can tell you it's unrealistic for the scope of this class because how do you heat it up? How do you heat it up?
Hair dryer. You send a signal to like hair dryer.
Hair dryer.
Hair dryer.
Oh, if
Like
it's temperature
make a
or if
box
it's
Yeah.
and have the hair dryer and like a fan and turn on the fan when.
Oh, a relay.
Yeah.
Yeah, that works. Okay, you have a very large footprint on the table to do it. Yeah, that works. And then after that, we had that little conversation. He was saying, so what if you use a finger to warm it up? Because I'm trying to let you guys use a temperature sensor that I have. These are all good stuff, just to let you guys know, okay? It's not some random things. It's always giving you more experience. So these, these are called NTCs. It's a negative whatever parameter resistor. I think negative means whenever the temperature goes up, its resistance goes down, I guess, or goes up. I don't know. So the positive is one direction, and negative temperature resistor is going to the other direction. So these are called thermistors, thermal resistors, thermistors. Super low cost temperature sensor you can get. So temperature changes, resistance changes. Okay. So given that, how could you get a temperature out?
So you send a current through them, or you set a set voltage across them, and then you measure the current that you're getting. So you know the resistance of the component, but then you use a table or a formula to figure out the temperature.
Mm-hmm. Temperature changes, this changes, right? Mm-hmm. Okay. So it's a voltage divider, so the analog voltage here will change depending on the temperature. And there's a certain equation that I can use to find out that, to convert that voltage into a temperature. Okay? So that voltage can be digitized by what? Something we're going to cover today. ADCs, right? So analog to digital converters. So digitize this analog voltage and using a certain equation to convert it to what? To temperature. Let me show the equation here. Let's see if I still have it. I have tons of projects. Sorry, I'm scrolling. Make you dizzy. Okay, so see here. You can, as a recorder, you can come to this website and look at this. It will be a good contribution to this educational efforts, because in the future, if I want to use whatever we have been working on in this class, in my class at Forest College, I'll probably develop another board. I won't use a Hall effect sensor and something else, but I will definitely include the temperature sensor and display module on it. So if you can figure out a way, for example, you propose what pins you want to use, you look at the GPLs, you tell me in the proposal, I want to use RA2, RA3, and the ADC AN4 channel to digitize this resistance output. See, it's just a very simple voltage divider, right? It's a little resistor or thermistor, and a 10K resistor eventually goes to ground. So the 5 volts ground dividing, and it's being digitized by the ADC of the Arduino ADC inside. So very simple project, and with the display on it. If you want to work on this project, highly recommend it, because I can eventually use it for the board I will teach in the class. This is one project you can use, very simple, and it's a good contribution. And the display modules should be the one here. Oh, I just posted to my website. I just updated. Order more. If you want to use it, let me know, okay? So there's a library I found online which works. On the laptop, I compiled it, it passed. It works in the computer. But I haven't downloaded it to the chip yet. However, that guy posted a lot of videos regarding the PIC microcontroller working with this OLAP module. Seems like there's a very good chance it's going to work. So I ordered, how many? 6 or something? I gave it to several of them. I still have 2 left. If you want to work on this display module, let me know. I can give you another one, since I want to work on it probably with one of them. I can immediately order more if I see that there's a demand in the class, want to work on this project. So get a temperature sensed, okay, using this guy, the thermistor, and with the OLED 1306 OLED display module. So what you want to do on the PCB board is, for example, here's a PCB, right? That's a microcontroller, that's a USB, whatever, okay? So there should be a female header pins, so you can directly insert this OLED display module to the header pins.
Did you know if SparkFun had like one of those OLED modules and you just drag in the
Oh, you mean the library?
yeah.
I didn't see there's a because SparkFun doesn't work. They probably don't work with PIC too much.
I saw that they had like it fits in a breadboard, so whatever the distance between each of those pins would be the same that you would use.
Yeah, these pins are almost the same. It's standard header pins. These are all universal header pin distance.
So for the display, we could use, you can use that with the PIC.
Yeah, you can use this one. I still have two. If you want to get another one, I can give it to you. And I'm going to order more. Next week, I can give you more. Okay? I believe I'll get it probably Tuesday. Okay?
I saw a bunch of libraries on Arduino, like Adafruit.
Yeah.
Is that the ones?
That's a standard one to use. I use that one.
Yeah.
Yeah.
How do you use them?
I don't know if you can use it with PIC. It could be because there are several different things. So the Adafruit library is mainly for the character formatting, but it's probably not for SPI library for PIC.
I looked it up online, and the guy's like, just do it in MCC. I'm like, where?
Oh yeah, there's MCC. It's a MSSP2.
Oh, okay.
Yeah, there's a SPI MCC module.
Okay.
Yeah. So, that's another good thing to talk about, right? SPI is another serial protocol. Yeah, and there's another one we'll learn this in the semester because these are the two most popular ones in addition to UART, okay? So during an interview, definitely you want to talk about that. If they ask you, like, have you worked with UART, SPI, or I2C, you want to take the chance to do it. So this semester will be one of the best chances that you can take to play with one of the, we have done this a lot, right? RxTX. So I don't think there's any problem with this one. But this one is for the SD card. Okay, if they ask you, like, which one's faster, which one's slower, which one's the fastest, you should know that, okay, as a digital engineer or electrical engineer. This is the fastest. What about this one?
Next fastest.
It's pretty slow, actually. You can adjust the speed by changing that pull-up resistor value. You can adjust the speed by writing to the registers to control it. With different speed, you need different values, a little bit different values of the pull-up resistor. Ranges from like 5K to 20K, I think. So why sometimes you need a faster one, you need a slower one? Why?
Sometimes slow is good enough.
Yeah, that's good.
Depending on what, like, the medium that you're transmitting over. So, like, for wires, you want a faster connection because it's hardwired. But if you have like radio waves or something even slower, then you want a slower transmission rate.
Mm-hmm. It depending on the applications, right? So for the SD card, it's pretty short connection on the board, and we usually use SPI for SD card communication. So we are getting into SD card application in Lab 9. If you want to apply an SD card module onto your PCB or in your project, you can start working on that Lab 9 a little bit now. And since you usually have like megabytes, hundreds of megabytes or even gigabytes of data to be transmitted. So usually we use SPI or SPI for SD card communication. For I2C, it's slower, but it's better for long distance transmission. Why is that?
With longer lines, you can come up with like impedance issues where they'll take longer for a line like raised high.
Yeah, impedance and parasitic capacitance, right? Because all these cables are wrapped with what? The rubber, whatever materials. So there are capacitors everywhere, even though they are not physical capacitors. But it's called parasitic capacitance everywhere. So it's basically the digital communication is charging and discharging those caps. They have time delays. So if you use SPI to transmit for over 100 meters, you won't be able to get good data. So whatever is going to happen is going to oscillate instead of getting full full value digital data, it's gonna like not charging up yet and then start discharging. You know what I mean? So they have time delays. So for long distance transmission, it could be a very good interview question. If I want to transfer a temperature data from a hot tub in Pagosa Springs over 100 meters cable to a data center being mounted to a pole on their property, right, 100 meters, do we want to use SPI or I2C?
Is it through a wire?
Yeah, it's a cable. Oh, temperature sensor, just a sensor, doesn't have microcontroller on it. It's just a little tip. I2C, okay? Long distance transmission. All right? We have the chance to play with this with SD card and this with accelerometer, okay? You'll be able to do both. It's good for the interviews. So always think about that kind of question, right? What kind of project you have worked with during undergraduate. You have done this, or this. So this could be one of the projects if you don't have any ideas about what kind of project you want to work on. Semester, I can order several, maybe not several, but 50 of them, like that, 50 probably, next week. And I'll order a lot of these OLED monitors as well. Very simple. So Thursday next week will be microphone, because the microphone is also sending out it's collecting my whistling and whatever is a sound wave, right? And that sound wave will be digitized by the ADC and eventually being stored in SD card. So you'll learn how to use ADCs. So this shouldn't be a challenge, because after Lab A, you will be able to know how to grab a ADC module from MCC and make this work, right? Then the only challenge is here, because we have other groups are doing this as well. So I think you have a lot of peers working on the same project, can help each other, all right? So if someone find out how to use it, definitely share, since I haven't got the library downloaded and applied to that yet as well. What's that?
So the boards we're making, are we getting them printed?
Yes.
Are they going to come assembled, or are we going to be assembling?
You have to assemble it. So I'm considering, depending on the schedule, okay, towards the end of the semester, if we get a board, but eventually we don't have the time to solder it, I may make the soldering optional for as a bonus points. But also now I think we still have a lot of time. Let's try to make it happen. Okay. It takes a lot of time. I have the PCB class has 100 students. I just got all the boards submitted. Every time JLC PCB only take 24 boards. I'd have to order like 4 times. Get a lab manager to order that for me, and there are so many different issues. I got emails from the engineer from JLC PCB saying this student, this, they don't know where that came from. So this PCB has short circuits here and here. So I have to zoom in and look at the short circuits and tell the student what's going wrong over there. And just one board. I got 100 boards, and there are probably 20 of them are having issues. So here will be better because we have pretty much like 40 groups. Will be 40 boards as a maximum. So I'll do my best, because I know a lot of students are very passionate about making a board. But if you are not, let me know. Okay.
Can we use bigger resistor sizes to make soldering easier?
1206 is already biggest in my mind.
Okay.
They are, like I told you, they are actually huge.
Okay.
Even though they are surface mount, but super easy to solder. So the ones I use is usually 0603. 0603 is it's 0603 is 0.06 inches by 0.03 inches. That's the smallest one you can handle, but you don't have to use that small. Use a small one like that. So usually, the one we have in the lab is 1206. So it's 0.12 inches by 0.06 inches. These are huge. I mean, super easy to handle. You just grab a tweezer, put it on there, solder it with the iron tip. So the tip can be as big as this one, as you can still solder it. But I believe they use the oven, so they have the paste put on the pads and use the oven to cure it.
I believe in Eagle, you're using, right, you can export DFM check settings. So it might be helpful to set up your DFM check to follow PLC PCB's guidelines, and then have everyone import it and run the DFM check.
Oh, you mean for the parts being popped up by them?
For the problems, to avoid some of them before setting them off.
Oh, I haven't done that before. Good to look into that. All right. So one of the projects you can use, right? Another one, so thermistor temperature sensing. OLED display. Another one you can consider. So I'm taking taking time from you guys, but thermistor here digitized. So use your finger to warm it up. Okay, so temperature goes up. So this is mimicking what? AC, right? AC temperature control. So for AC, a cooling system, it doesn't care about heating it back, right? So AC is just cooling it down. So in that case, you don't need to heat it up. It will make things easier. So what's happening is whenever you warm it up, use a finger, it's getting warmer. ADC samples it and eventually send a signal to what? To a fan. Okay? To a fan. So how to make a fan work? So this one will go to the PWM module and output PWMs to control motor. So this will get into a motor's. The motor's name is L293. It's a good experience to have. If you want to do that, I'm gonna support you. Okay. So here's a tutorial on how to use that chip. Super simple. Promise you. Even high school students are able to do it. So the connections are super simple. You got DC motor, you connect to these two pins and enable it. And this is logic on and off, so you can use PWM to control it. So you can control the speed of the motor. So whenever you warm it up, the temperature goes up, you just use the PWM to feed it back to the motor driver, and eventually the motor will turn faster. Okay, that's another very good project for this learning board moving forward. So everything can be demonstrated on the breadboard first. I'll get you the motor, get you this chip, super simple, the dip version, plug into the breadboard, connect to the motor, and we have the PWM ADC on the pigboard. It's gonna work. No problem at all. So you can talk about the motor control. Okay, motor control as one of the projects you have done in undergraduate. This is project 2. Also, other students proposed really good ideas. For example, yeah, hopefully you don't mind I share these ideas, because if more students working on it, we just get a better chance to make something to work, okay? So sound wave comes in, it could be whistling, all right? You have different people whistling, has a different frequency. And in lab 8, we'll learn how to detect the frequency of the whistling or sound wave, whatever, being sampled by what? By the microphone. And then ADC, all right? So what you can do is use the frequency to control the PWM's duty cycle, and then control the brightness of the LED, the RGB LED. All right, you can split that data here, the frequency data here, and use it. For example, this frequency I want to show a blue color. This frequency I want to show a red color. This frequency I want to show a yellow color. So like different, you let your friends whistling and see who can get a different color, can get what kind of color, right?
That's kind of cool.
All right, make sense? This can be a very good project because you're combining 2 different modules. What we have learned before, okay? So,
have you watched Guardians of the Galaxy?
You've never watched Guardians of the Galaxy?
no, it's a show.
It's a movie, and this dude has this weaponized arrow he controls with his whistle.
Uh-huh.
So
You could have something that rotates, and depending on the pitch, it rotates a different way.
Or I was
something
thinking
down.
mix the whistle decoder with the motor before, and
Yeah.
maybe make a skateboard or something powered by your whistle.
Yeah, that's interesting.
No, it's you just glue together those two projects.
You got
with-
powerful
with
whistle?
four motors. With
Cool.
4 motors, and I'm not saying a full scale, but I'm saying like a mother.
You can connect digital system to anything, right?
I'm
You
saying
can connect the digital system to
and then like 4 little motors.
like a switch in the room. Your whistle, all the lights are on.
That'd be
And another way to do that is see whose whistle can trigger the different brightness of the LED. So depending on the amplitude here, right?
yeah.
You have a louder whistle, you got a brighter LED,
So you PWM.
right? Oh, Peter, you can do you can change the duty cycle here, make it wider. Okay.
So we take the individual whistle, change the PWM.
Any question on this?
Why do we use an active high LED on our
Yeah, that would
board,
just
or active low?
I was thinking just go
Because
forward.
it makes more logical sense to like program PWM when it's
Yeah.
pulsing a 1.
Yeah.
And it should be a 1.
Doesn't really matter, I think. They both equivalently exist in all the designs. I
think that'd be pretty cool.
not a big deal here.
We can tape an arrow to call it.
All right, one more project. If someone can do it, I can waive your PCB task. Okay? The embedded system class here doesn't have a PID control, which is not perfect. So you need a PID control for a lot of things in the real world. Okay? So when they are doing interviews, you tell them you have done PID control. That's a huge plus. I can tell you. Let me see if I have something to show you. I don't have it here, probably. No. So PID control is a feedback system. Can be used to control temperature. Can be used to control motor as well. So if you have the experience to work on both, that'll be a slam dunk to get a job. Okay. So why it makes sense to control motor though? So for example, I have a 2-wheel robot car. Okay. It won't be able to stand on the ground by itself because it's only 2 wheels. Okay? And I have an accelerometer on the top, which is able to sense the angle of the car. So whenever it's tilting toward forward, it's able to sense the angle and trying to pull it back. How to pull it back? Roll the motor forward. Okay? So when it's leaning backwards, it's able to roll it back as well. So the digital system can do it really quickly. So what's really happening is a dynamic control system like this. You know, eventually the 2-wheel robot car will be able to stabilize itself and standing on the table. That's a really good project to work with. I don't think you guys will have the chance to do it unless you are working on this project in senior seminar. However, we are not doing that kind of large scale of project over here. But however, you can work on PID controller with a very simple program. Trust me, super simple program. But the thing is, we haven't covered that in the class. If you want to work on this one, just get the equations implemented in the C code. It's not really long. You can see the Arduino ones. It's the same C code. It's not long at all. That's it. That's a PID controller. You can implement it and use it for LED brightness control. Think about it really quick, how that works. Given that this is a light sensor, it's a photon sensor, it's very simple, it's called LDR. It's a light-dependent resistor. You got more photons, you place it in the brighter room, it's getting lower resistance. If you put it in the dark room, the resistance can be as high as 10 megohms. And the resistance decreases very quickly whenever you give a little bit light on it. It almost decreases to 0, only like 30 ohms if you have something lighting up just next to it. Okay? So what you can do is you set up a brightness level of the LED in your program. For example, I want that brightness to be because this reading will be digitized. It's the same thing as the resistance and another resistor here, so it's a voltage divider. So you're reading a voltage here and being digitized by ADC, right? Make sense? That's a light dependent. It's not temperature dependent right now. It's a light dependent. So the resistance reflects the light intensity in the room. So you can digitize that voltage signal, okay? And you can set a set point. If you work on this project and implement it with PIC, you don't have to do the PCB, okay? You can test it on the PIC board you have starting next week. So for example, this is LDR, light dependent resistor. It's giving you a reading here. That's a set point. Okay? And you have an LED over here you can manage. You just turn it on, you test it first, you turn it on, you see the signal comes here, drops to here. If you turn it off, the signal comes back to here. Okay? So what you can do is use a PWM waveform instead of just simply turning this on and off. You can use a PWM, an adjustable duty cycle, to control the brightness of this guy and adjust it. So eventually it's not overshooting, it's not undershooting, eventually it's stabilized at this brightness by using that feedback control. That's the easiest feedback control you can apply to a microcontroller using PID. And that'll be a really good project you can talk about during interviews. Make sense? No motors, nothing else. Just two resistors plug into the breadboard. Work on that algorithm. Implement it to PIC. Done. Adjust it, all the PID gains. So you can learn how to do it by searching in Google, do anything else. As long as you spend effort, you take efforts into this project, you do the set point, you do the adjusting. Even though that eventually it's not perfect, I'll still give you partial credits, maybe 90% or 95%. Don't be afraid of failures, all right? Just take the challenge. Take the challenge. Who cares, right? After 6 weeks, I'll go back for Christmas break. You guys will done for the semester. Who cares, the failures, right? Just take the challenge. Just do it. You do it, you grow. If you don't do it, you never gain in knowledge. Don't be afraid of anything. Just do it. Nobody cares, right? So what really matters is eventually you'll learn something, okay? If I see you are take the efforts, I'll give you a lot of partial credits. Keep that in mind. What I want to see is not really it's functioning. Definitely that's the case. If it's not functioning, but I see that you are taking efforts, you are asking questions, doing a lot of critical thinking and design, you got a lot of partial credits. Keep that in mind, okay? Doesn't matter. 10 years later, I'll retire. Who cares? Just do it, okay? So the PID controller, if you want to do that, no PCB is required. Also, for other projects, if you think your project is complicated enough, tell me, write into the proposal. I'll grade the proposal after Wednesday deadline. I'll look into it. If you can justify that it's complicated enough that I don't want to do PCB, you hate PCB, which is fine. Okay? I'll waive it for you, but it has to be complex enough. Okay? I have to approve it. So write into the proposal, I'll read it after Wednesday next week. Any questions on this?
Do you have like female to female jumpers for breadboarding? Okay, never mind.
Male to male, right? Female to female? Male to male, right?
Female to male then.
Oh
You
yeah,
have the pick.
yeah. I can order more. Yeah, I can order
I
that.
don't know, we might have.
Okay, cool. Let's go through ADCs really quick. ADCs is really simple stuff. So what I heard is the labs in the future. No, not the labs, but the lectures afterwards are pretty simple compared to the previous ones. So they said Lab 6 and Lab 7 are the most difficult one. After that, it's getting a lot easier, and I totally agree with that. Because if you look at inLab08, look at ISR. Look at ISR. Only like 5 lines. So within the 5 lines, The first one is the test pin, and the last one is the test pin. Only 3 lines. So within the 3 lines, one is the flag, one is the timer. So basically, only 1 line for ADC in the ISR. Easier, a lot easier. So let me go through the ADC math really quick. What? Math?
What's when you have like blue on your PCB?
Uh-huh.
Is that bad?
Say it again? Say it again?
The bias. You have a lot of bias.
Oh, vias.
Vias.
Yeah.
Is that fine?
You want to reduce the number of vias as much as possible. If you can now avoid it, that which is okay. You can place parts to the bottom of the board if you want. You know what I mean? Then you can reduce the number of vias. So it's easier to route. It directly drill a hole. Any questions? Any questions before I move forward? We'll cover ADCs and the lab08 stuff today and Monday week as well. That's the plan. Okay, that's the plan for today and next week, early next week. So ADC is a device has 1 input and how many outputs? Depending on what? Very important module. For example, someone asks you, have you used an ADCs in any projects? You say, yes, I used it in the embedded system class. It's embedded, it's an internal ADC of the microcontroller, and they'll ask you, what's the resolution? Okay, that's usually what the questions are. What's the resolution? So the answer is 10-bit or 10 bits. It's a 10 bits. So this ADC has 10 bits. It's a 10-bit resolution. What does that mean? So ADC will define a range. Normally, the power supply and 0 volts as an entire analog input range that it can resolve by the ADC. So 10 bits will be all the little stages to resolve that whole range. Does that make sense?
So it has like 10 steps?
2 to the 10th.
Oh, 2. Oh, yeah.
It's like, resolve it, right? Okay? So how many steps?
2 to 10.
Is what?
1028, 1024.
Okay? From 0 to what? Cool. If I tell you that's the whole range, what's the voltage level for each step?
Like 3.3 by 10.
Yeah.
Divided by what?
1023. 1024.
Yeah.
What is that?
Very small number.
So this is 1,000 something. What is this? It's 3.3 volts.
Yeah.
So 3.3 volts divided by 1,000, what's the smallest voltage you can resolve?
3 millivolts.
Yes. Resolve. If there's a signal comes from the sensor, okay, it's varying within like 1.2 millivolts. There's a sensor. And that's critical. You have to resolve that voltage because it's an ECG detector, okay? The ECG detector detecting your electrocardio signal is usually like only 1 millivolts or even lower, okay? Okay? Do you think you use a 3.3 volts range and with a 10-bit ADC will be good enough or no?
Probably should.
Yeah, someone is dying, you still couldn't see any difference, right?
Their heart's
Cannot
going,
resolve
you
it.
shock
What's that?
them anyway.
Could you, I mean, if you had to use these sensors though, could you feed it into an amplifier and then after that use the sensor?
Yeah, but still, even though it's amplified, yeah, they have to be amplified first.
Well, I'm saying like that amplified then into the sensor. Like you amplify the signal first.
You amplify it first, yes, you have to amplify first, right? So they have to be pre-amplified. So from this to this, right? You have to amplify within that range.
Right.
So the thing is, a 1.2 millivolts change being amplified by 100 times was voltage here. So
120 millivolts.
yeah.
So then you would be able to detect that with the.
Yeah, so have to be able to resolve this one in order to detect that, right? So
Right.
there are a lot of cases like even here amplified is already it's still smaller than here.
Oh,
Then that will be a problem, right?
then that is a problem.
Yeah, but that's just a concept. If you see a signal which is within the range, is smaller than the range of the smallest signal and resolve, what you can do,
Get a higher resolution.
just get a better ADC, right? There are 12-bit, 14-bit, or even 24-bit ADCs. Okay? Make sense for this? So this similar kind of calculation will be put on the grade booster next Friday. In-class exercise,
In class.
aka grade booster. Bonus points. You're like, I don't believe you.
1%.
You're not losing points. It's not counted towards your grade, okay? It's just boosting your grade. So let me give you some examples, okay? Let me give you some examples. So ADC reads the value 842. Is that reasonable? What is the V in?
842 times the resolution.
Is it reasonable? ADC reads the value like 800. You can read until like 1024, right?
Is that a 10-bit ADC?
Yeah, 10-bit ADC
Okay.
and 3.3 volts range. Okay. What's the V in? So the equation you want to use is 3.3 volts divided by 2 to the 10th. That's a ratio for what? What's the unit here?
That's how many volts.
That's the resolution, right? How many volts per what?
How many volts per whatever the thing on the bottom is. Per bit?
Per bit, yeah.
Yeah.
Yes, per LSB
Yeah.
or per bit. Yes.
Per channel.
So it's volts per LSB, right?
So then multiplied by 842, which would be.
Yeah, let's just list it in a form like this. So at the bottom is what? Digital, right?
Yeah.
Digital value. So digital value here. On the top is what? V in, analog input. That's it.
Mhm.
So all the ADC math on the website here for multiple lectures is everything about this equation. That single equation. And there are some errors here. I'm going to talk about that on Monday.
It's just.
So something is wrong here. But anyway, so let's figure this out first. Does that make sense? If I give you this and ask you this, you can still use the same equation to calculate it, right?
Yeah.
It's going back and forth. So I'm gonna mark it, okay? Great booster question next Friday. Okay? Let me see. Okay, one more thing you need to know. Any questions on this before we move forward? Does this make sense? Yeah, you guys? Just very simple equation, division here. So the range can change depending on the value given by the problem. And they are even adjustable. I believe there's a register to control it. So if they tell you the range here is 3.3 volts, and there's a name for it, it's called Vref. It's a reference voltage. Okay? If they tell you the range is from 0 volts to 3.3 volts, so you directly use 3.3 volts here, right? If they tell you that you can put a register and control the lower range here, so move it to 1 volt, so the total range becomes what? 2.3 volts at the reference. So you want to put 2.3 volts over here instead. Make sense? Make sense? Okay. Okay, now let's get to the code really quick, so we can finish whatever I was trying to cover today. Look at the inLab. Super simple. We just need 2 minutes. We have 3 minutes left. We only need 2 minutes.
Let's go.
Okay? inLab08. Super simple. You see? Nothing tricky here. Whenever someone press S, it's gonna start sampling. It's gonna, however, during this process, interrupt is always on. So it's always getting to the interrupt to do what? Sampling, ADC sampling. So there will be a certain frequency to sample that data from the microphone. Let's get to it real quick. What does sampling mean? Sound wave comes in, it samples points, discrete points. Okay? Here's
Hoping R5, because R5 is connected to ALM4.
so the microphone is is detecting it.
Start whistling.
That's sexy. That's really sexy.
I didn't even know myself is a function generator before. Sound wave generator. So pretty. The sound wave is so pretty, right? It's amazing. All right. So it's sampling. It comes here, and this one samples it. That's it. So gets into this interrupt every, let's say, 100 microseconds. Sample it, and then comes and then go back to wherever it was, right? And then 100 microseconds later, come back to SR, sample it. That's it. You don't even need to do anything else. Everything will be mastered by this function. All right, we'll talk more about it on Monday.
Thank you, Professor Lee.
Yeah.